Okay, so the last part of this chapter is on numerical solutions for advective diffusive equation, which we already saw. We derived it just to show how diffusion terms are added, and then we looked at numerical diffusion that is introduced by numerical methods. So we'll cover that and then close out this chapter. So here is a general form, a dc/dt, again a tracer advection equation with a diffusion term in one-dimensional form, d del squared c del x squared, if you remember, that's how diffusivity works, plus u dc dx, the advection term, but here an additional term has been included as a source term, which is dependent on the concentration that's already present. So this can make for some interesting numerical issues as well, which is not really discussed much here. So writing this as again a implicit method, so there's n plus 1 here and n plus 1 here, but a parameter theta is included here. So looking at dc/dt, this looks like the Euler forward cm n plus 1 minus cmn or delta t, but becomes implicit because on this side you have d times theta grad x squared cm n plus 1 plus 1 minus theta grad x squared cm n divided by delta x squared. So that's the second derivative there, plus the advection term u grad x cmn or 2 delta x, so another central difference there, plus b times c at m and n. Here theta in this equation is a free weighting parameter which ranges from 0 to 1, defining the degree of implicity of the scheme. For theta equal to 0, the scheme obviously becomes explicit, and the right hand side of 3.54 has no time index n plus 1, so that term drops out. The explicit scheme is stable for d delta t or delta x squared less than equal to 1/2. So with the diffusion term, the Euler forward becomes stable under some conditions, even if you remove the implicity. Then you write the grad x cmn as a central difference. Grad x squared cmn is of course again a cm plus 1 n minus 2 cmn, so either side, and then the central point obviously gets divided by delta x squared. For the parameter combination u equal to 0, b equal to 0, and theta equal to 1/2, then this equation here, theta equal to 1/2, the equation is called Crank-Nicolson scheme. So it's a specific numerical discretization method for this advective diffusive equation. All these methods typically are put through a test for convergence, numerical diffusion, and ability to capture sharp fronts and so on, and you can find those in books that are focused on numerical methods like Anderson and Fletcher, which is an old one, but there are now many new ones. So this is Crank-Nicolson is absolutely stable for u equal to 0, b equal to 0, and theta equal to 1/2. In general, the stability of that equation requires that d times delta t or delta x squared is less than equal to 1/2 times 1 minus 2 over theta. So if theta is 0, then you get the condition that we saw here for the explicit scheme. If theta is some other value, so here it has to range from 0 less than equal to theta and less than 1/2. So that's general stability. If you want absolute stability, then theta has to be greater than or equal to 1/2, which makes it more implicit. So remember, this is implicity range defined by theta. So how much of the future time step plays into the solution? Of course, you end up with the other issues like matrices and inversion and so on, but it guarantees stability. And as you remember from before, numerical diffusion will still be an issue, but you can use a larger time step and save on computing time, which is the advantage of implicit method, that it is stable for a larger time step without changing the character of the error. So that then brings us to numerical diffusion as the last section. So let's look at our advection advection equation again, and the wave equation d squared c dt squared minus u squared d squared c dx squared. So you can write solutions again as Cm plus 1 n equal to Cmn plus del Cmn del x delta x. So we are writing basically Taylor series expansion for m plus 1. So 1 over 2 factorial del squared Cmn del x squared times delta x squared, and higher order terms which determine how many of them you include determines the accuracy of the scheme. And in time, similarly, you have Cm at n plus del Cmn del t plus 1 over 2 factorial del squared Cmn del t squared times delta t squared, and higher order terms. We've seen these before, so we plug these into the discretization and end up with something like Cmn plus 1 minus Cmn or delta t plus u dc dx written as m plus 1 minus m. Minus, we keep the approximation terms here as 1 over 2 factorial del squared Cmn dt squared delta t minus u times 1 over 2 factorial del squared Cmn del x squared delta x, and higher order terms. So that's our 357. Then 358 can be written as Cmn plus 1. You express this also in terms of combining them to look at so the same terms here, and we are writing this as minus 1/2 u squared delta t plus 1/2 u delta x times del squared Cmn over del x squared and higher order terms. Why did we do that? Basically to show numerical diffusion. So this is our numerical diffusion term, which is dependent on u, delta t, and delta x. As we said before, delta t and delta x cannot be chosen completely independently. There is always the CFL condition to worry about, and the compromises between spatial resolution and time stepping, they often tend to be tied together as well. I included one example completely randomly picked from internet. So this is from this paper, which is looking a metrological problem, but here this is just an example. What happens when you have numerical diffusion that is unacceptably high? As we saw, the peaks get damped and spread out, dispersed and damped and diffused. So there are methods involved mostly in aerospace engineering, as I said, which do what is called flux corrected transport. So transport is of course the terms we are talking about, UDCDX terms, and you want to maintain the distribution of the tracer or temperature or whatever you are trying to simulate or forecast, and flux corrected transport basically tries to correct for numerical diffusion by putting them back in. So there is numerical estimations and advections of fluxes to be correcting. So you can see some of that approximately here. So this is showing some 2D field after subjecting to a regular fourth order. So it has issues at the boundaries, as you can see, compared to these, for example, in terms of the distribution. This is regular sixth order, so it improves some things but also introduces other issues. You can see the distribution changes. And then this is the fourth order flux corrected, so it has removed all these errors, false maxima and minima at the edges. You can think of those as improving boundary conditions. Sixth order flux corrected scheme, there are metrics where you can see this region is reduced, so you've improved the simulation, and these are other methods where it's simple sixth order with simple flux limiter diffusion scheme, and this is the fourth order and sixth order simple flux delimiter diffusion schemes. So I'm just including this to say that when you are trying to simulate climate processes, either as coupled ocean, atmosphere, land processes, or just the ocean or just the atmosphere, especially when you include chemistry and so on, you need to worry about these details of how transports affect the distribution of tracers or active quantities like humidity and temperature, and you have to worry about maintaining certain features that are critical for the prediction and for simulation. Okay, so that closes out chapter 3, which is a rather brief introduction to the various numerical issues we face even when we consider a simple thing like linear tracer advection equation or advection diffusion equation. Okay, so we'll move now to actual transports in the real world.